Welcome to the presentation on principles of magnetism and electricity. This presentation offers a very light introduction to the phenomena of magnetism and electricity. The important takeaway from this presentation is the general ideas and concepts. No math will be used in these slides, but we will highlight the relationships that are easily shown in simple ratio and proportions. The intent here is to give you a visual understanding of these phenomena. History has to give somebody credit for everything. So in this case, Thales, a famous Greek, some 2,500 years ago, noticed that after he rubbed a piece of amber with a woolen cloth, that the amber would attract lightweight items such as dust, straw, feathers, and lint. I'm guessing that he was probably polishing pieces of amber for the marketplace, and he was using a woolen cloth. This same principle can be discovered on a daily basis. I remember one time I was sitting in a restaurant, and when I eat by myself, I have nothing better to do than play with whatever's in front of me. So I picked up the sleeve that my straw came in for my soft drink. I held one end in between my thumb and forefinger, and then I took my other thumb and forefinger and slid it along the length of the sleeve to flatten it out. I was going to fold it up or tie it in a knot, I can't remember now, but after sliding my fingers across that sleeve, when I brought my hand near it, it was attracted to my hand. That is static electricity. Our modern term, electron, is the Greek word for amber. So this is one of the many examples where the actual meaning of the word has no relationship to how it's used today. Quite a few years later, a cat named Dufay, actually in 1733, found that if he rubbed against a piece of glass, the glass and his fur would become charged or electrified. He also found that the charged glass would attract certain things that his fur would repel or push away. From this experiment, this cat decided that there were two elements of electricity and they were directly opposite. Although I'm sure that this is not the first instance of this discovery, it was almost 800 years later that it was discovered that the same phenomena was observed when other dissimilar objects were rubbed together. It was also noted that not all affected objects were attracted to each other. Some repelled away when brought near, and some were attracted when brought near. This is the origin of the concept of different types of static electricity. Personally, I never know whether or not to really believe this account or not. However, it's so widely accepted, it probably was true. But we've all heard the story in American history where Ben Franklin went out into a thunderstorm and flew a kite, and he had a string tied towards the bottom of the kite with a key hanging on it. And when lightning struck the kite, the key lit up. It glowed. This is not impossible. Nonetheless, we'll just take it at face value. Well, Ben Franklin decided that the two elements of electricity should be named positive and negative. Now remember that he's supposing this from observable phenomena. He cannot actually see what's going on. So he surmised that there was something named positive and something named negative. Positive meaning an excess, negative meaning a deficiency. And these are the commonly referred to as plus and minus, or shown graphically as plus and minus symbols. And he surmised that there was a flow from an excess to a deficiency. And since positive is excess and negative is deficiency, he determined that this flow was from positive to negative. This was and is referred to as conventional current flow, from positive to negative. However, much later, when electron flow was discovered, it was discovered that the actual excess is an excess of electrons. And in the meantime, they had designated an electron as negative and an atom missing an electron as a positive ion. So the two were in conflict. So conventional current flow is called conventional because it goes back to Ben Franklin and electricity flowing from positive to negative. Whereas in reality, electron flow, the actual flow from excess to deficiency, is from minus to plus. And some schools teach conventional current flow from plus to minus. Other schools teach electron flow from negative to positive. It really doesn't matter because you can't see the actual movement anyway. So it's basically terminology to describe observed behavior, but not actually observed physical motion of something. I'm sure everyone listening to this presentation can provide multiple accounts of personal discovery of static electricity. Some of it benign, some of it humorous, and some of it maybe even painful. I remember I was walking through Disney World inside a building, and I noticed that there was a lot of static electricity. The atmosphere was just right, and dryness and what have you. And every time I got my finger near anything metallic, a big arc would jump off the end of my finger. So I was walking along with a friend and his brother, and I scuffed my feet really good, got a good charge going. I reached around behind my friend and put my finger up behind his brother's ear, just close enough to get a big arc. It sounded like a snap, like breaking plastic, and boy did he jump. Now you probably think that's mean, but anyway, not bad as Reuben here, because eventually that static charge is going to dissipate and down those babies are going to come. This list is called the Triboelectric Series. If you read down through this list, human hands, usually too moist though, are very positive, down towards the middle, steel, which is neutral, and down towards the bottom, Teflon, which is very negative. So through the years of experimentation, this list was put together and the order verified. So some objects, when rubbed together, display a very strong force, while others are very weak. As objects of different composition were experimented with, this list evolved. Today this list is as you see it here on the screen. The materials at the top in red text have been determined to give up electrons to the materials lower in the list. Yes, that means that when you rub glass and fur together, you get a static charge even though they are both in the upper half of the list. Another example would be silk and cotton. They're both in the upper half of the list. If you rub silk and cotton together, and ladies have probably discovered this more than men, wearing a cotton undergarment and then a silk blouse, but this combination is available for the guys too. And maybe you were undressing in the dark, and as you were pulling off your silk blouse, you felt some static discharges and maybe even saw the sparks. Many of us have been known to do this in the dark just to see the sparks. Now, if you take silk and rub it against glass, the silk is now negative compared to the glass. So it's the relationship of plus to minus is determined by where they're at on this list. The higher on the list, the more positive. The lower on the list, less positive. So in the first case of silk and cotton, cotton rubbed against the silk stripped electrons off of the silk, leaving some of the atoms in the silk missing electrons and therefore positive. Whereas when silk is rubbed against glass, the silk actually rubs electrons off of the glass, and the silk is now negatively charged with an excess of electrons, leaving the glass missing some of the electrons from the outer orbits of its atoms. So it is proper to say that the silk is more positive than the cotton, and yet less positive than the glass. So the most positive is positive, and the least positive is therefore negative. The same rules apply throughout the list, top to bottom. So at this point you should be realizing that electricity is the separation of charges. An atom, electrically neutral, has an equal number of positive elements and negative elements. But if you remove one of the negative elements, then you have more positive elements than negative elements left behind. Therefore you have a net balance of positive. And whatever device took the electron away, it now has an extra electron, therefore it's negative. So producing an electrical charge by creating friction between two dissimilar materials off of this list was the first method discovered to produce electricity, and everything else followed as people became more familiar with the phenomena. Now remember, this was discovered, we'll say, by Thales the ancient Greek, and then he showed it to friends, and eventually this gets around, people play with it and they experiment, and then they draw conclusions. So a lot of what is known about modern electricity is still based on those basic conclusions. This older gentleman here, Dmitri Ivanovich Mendeleev, is basically credited for the periodic table. And we give a date here of 1869. This is just to give you a chronological reference. And the idea of the periodic table evolved because it was discovered that not all atoms are alike. Everything is made of molecules, and molecules are made up of atoms, but not all atoms are alike. For instance, H2O, water, 2 atoms of hydrogen and 1 of oxygen. Oxygen is a heavier material, has more components in its nucleus and more electrons orbiting the nucleus. So not all atoms are alike. This periodic table really is the work of more than just this gentleman. There were hundreds of scientists that really contributed to this periodic table. And the reason they call it a periodic table is because they have arranged them to show the periodic similarity as you go through from the lightest, which is hydrogen, the lightest, which is hydrogen, to the heaviest, which is down in the lower right hand corner. So it goes from the upper left hand corner across to the lower right hand corner. And so they pick this number of columns because as you go through the elements from the lightest to the heaviest, periodically one of them displays similar characteristics to one of them earlier in the list. So if you look at hydrogen, it's yellow, and then right underneath you have a column of green, then blue, then you have a number of columns of orange, then you have red, yellow, cyan, and back to blue. Of interest to us, because we're talking about basic electricity, are copper, silver, and gold, Cu, Ag, and Au. Copper is the lightest of the three, silver is medium weight, and gold, of course, is the heaviest. Everybody knows gold's heavy. What is similar about these three is that each of them, in their outer electron orbit, called the valence ring, have only one electron in that outer orbit, and it's loosely attached to the atom, which means it's easily stripped off for the movement of electrons, hence they're called conductors. Another vertical column here would be silicon, germanium, and selenium. These are 3 elements used to make semiconductors, and of course silicon now is the most dominant of those. So the periodic table here is more than just a list of elements. Conductors and insulators are extremely important to our understanding of basic electricity. If you want to control the movement caused by applying an electromotive force, you need to have influences that oppose it going where you don't want it to go, and you have to provide a path for it to go where you want it to go. It's something like digging a ditch to drain a pond. You dig the ditch to get the water to go where you want it to go. So the size of the ditch would be an insulator, and the depth and altitude of the bottom of the ditch would be the conductor, so to speak. So a brief examination of the apparent structure of atoms will assist in your understanding of both insulators and conductors. Atoms are proposed to be made up of a nucleus around which electrons travel in orbits of defined distance, and each level of orbit contains a definitive quantity of electrons. The outermost orbit level is referred to as the valence level or valence ring. If the particular element, such as copper, the one that we're most interested in as a conductor, happens to have only one electron in its outer orbit, it is classified as a conductor. As the quantity of electrons in the outer orbit increases, they are more tightly bound to the nucleus. So an element like silicon, which has 4 electrons in its outer orbit, is classified as a semiconductor or an insulator, and copper, which has only 1 electron in the outer orbit, is classified as a conductor, because that lone electron is not tightly bound to the nucleus. So we'll look a little deeper at the conductive properties. Niels Bohr introduced this model of an atom back in the early 1900s. And I want to say at this point, and I will probably repeat myself a couple more times, no human being has ever seen an atom. That is to say, no human being has ever had the image of an atom focused on his retina, whether it be from a lens microscope. The reason that they say they can see atoms with an electron microscope is basically they throw energy at an element, and then they look at the reaction and determine what they're looking at from the reactions. Kind of like reaching your hand into a dark hole where you can't see anything, and then moving your hand around in there to see what happens. You can feel with your hand, you say, oh, okay, this feels like this feels like that, therefore what's in there must be a dog, because when I pet it, I can feel it wiggling, so it must be wagging its tail. So if you've never seen a dog before, you'd really have a hard time reaching in a dark hole, feeling something warm and furry and petting it and saying it was a dog. So remember, no human being has ever seen an atom before. So this model that you're looking at here, the Bohr model, represents a nucleus which is to represent the bulk of the mass. And a nucleus is made up of protons and neutrons. Orbiting around the nucleus are a number of electrons equal to the number of protons in the nucleus. A proton is positive, you see the nucleus there, plus 29, and then there should be 29 negative electrons. And those electrons have energy, and if they had no energy at all, then the electrons would collapse into the nucleus, and the two charges, the two electrostatic charges, would come completely together, then cancel the field. So the electrons actually have energy, and they're trying to move away from the nucleus, but the positive charge in the nucleus is holding the electrons from going out any further than what is shown here. This is a little bit different model of an atom, but it's still a Bohr model. It just has a little dimension to it. This is a newer graphic showing the Bohr model, and the valence electron is emphasized as a light green ring. So that is the valence electron, or the electron that can easily be freed up if you apply a force. Now, that force doesn't have to be magnetic or electrostatic. It can be thermal. If you heat up this atom, the electrons become more agitated, and this free electron will fly completely out of its orbit and then drop back in. So they call that thermal emission. So almost all objects have some thermal activity, even at room temperature. At some point, we've all played with magnets, whether it was the magnets on the refrigerator, or we paid particular attention to them in science class, or magnetic things that we come across in our daily lives, and we stop and play with them for a minute. Well, what is magnetism? At the heart of magnetism is the electron. The electron is presumed to have a magnetic polarity, just like the Earth, and the electron has a spin. Like the Earth spins as it orbits around the Earth, electrons spin as they orbit around the nucleus. If you've played with enough magnets, you know that depending on how you hold them against each other, in one direction they attract and hold tight together, in the other direction they repel. So every atom has electrons. Every electron has a magnetic field, as seen here. And by the way, they show the magnetic field as lines. The lines are only to depict that there is a magnetic field there, and if it's comparative, then between one object and another, the denser the lines, the stronger the magnetic field. But theoretically, these lines of force, or flux as they call it, magnetic field, actually extends out indefinitely. So if you took two of these electrons and they were facing opposite directions, in other words, their spins were in the opposite direction, as you see here, the spin of the electron determines the polarity. And if you look at those magnetic lines of force and look at the direction of the arrows, you'll see that the lines leaving the North Pole on the one on the right are traveling in the same direction as those going into the South Pole on the electron on the left. So these two magnetic fields cancel each other out completely. So although every electron has a magnetic field, in almost all atoms the net magnetic field is zero because the electrons balance each other out. However, in one material in particular, and that's iron, and we refer to it as ferromagnetic material, the way the electrons are orbiting around the nucleus, they don't all cancel out. So every atom of a ferromagnetic material has a net magnetic field. Remember, all other materials have zero magnetic field because their individual magnetic fields equal and they're flipped in opposite directions and they cancel. Only in ferromagnetic material do all of the atoms have a net magnetic field. However, if you take two ferromagnetic atoms and place them next to each other in opposite directions, then they too cancel each other out. So iron, or ferromagnetic material like steel, a nail, a screwdriver blade, etc., they are ferromagnetic material, but because their atoms, which make up their molecules, are arranged in random directions, you get a net balance of zero for the magnetic field. So if you've ever made a magnet, meaning you've actually magnetized a piece of iron or steel, this is how you probably did it. You wrapped some electrical conductor around a nail or a screwdriver blade, and then you touch the two ends of the wire to a battery, and as current flows through that conductor, the electrons flowing through the conductor, since they're all going in the same direction, their magnetic field joins together to make a very intense magnetic field inside of that coil. And inside of that coil was that nail or that screwdriver blade. That forces the molecules in the ferromagnetic material, called domains or dipoles, meaning two poles, it forces them all to line up in the same direction. And then when you remove the magnetic field created by the wire wrapped around it, not all of them go back into random order. So it's left with a net magnetic field, and now you have a permanent magnet. Now, in manufacturing, when they make a permanent magnet, they take ferromagnetic material in a semi-molten state. In other words, it's not quite a liquid yet. It's still a solid, but it's very, very malleable. You know, it's red hot and just below the temperature for making it, melt into a liquid. They place it inside of a really strong electromagnetic field, created by electricity flowing through a coil, and by a conveyor, it goes into that field, and the magnetic force from the coil with the electricity running through it forces all of these domains, the ferromagnetic material molecules, it forces them all to line up with all their north poles in one direction, south poles in the opposite. At that point, it is a very powerful magnet. And then while it's still hot and being magnetized, they quench it with water, and so as the metal hardens again, all of the domains or dipoles are all lined up in the same direction, and now you have a really powerful permanent magnet. So when you go back to this picture, you can see that the source of magnetism is the electron, even though we think of a magnet as a bar magnet with a north and a south pole. It's actually comes from the electrons that have not completely randomly balanced each other out to a net zero magnetic field, but instead they have a net magnetic field. This is a no-brainer. Opposite forces attract, like forces repel. And this is evident in nature as well as in physics. Physics is actually kind of a contraction for physical philosophy. So physics, the study of physics, the science of physics, is physical philosophy. So opposite forces attract, like north and south poles, like forces repel. And this goes for positive and negative. Positive repels positive, positive attracts negative. Okay, here's two charges. And we're just going to further emphasize what we've been saying. Notice that the lines of force emanating out from these charges, one negative, one positive, are traveling in opposite directions. So if you place two like forces next to each other, as seen here on the left, their lines of force, or their flux, joins together and draws the two objects closer and closer together. So the lines of force are always seeking to be as short as possible. So in this case, this negative and positive charge would come together, and then the magnetic field would cancel out. The force is still there, but it's canceled out because it is trapped between the two. Now, put this in your mind for pondering. Let's say that you took this positive force and this negative force, or this positively charged object and negatively charged object, they're also called ions, and you put them near each other, but you did not allow any means for them to come closer together. In other words, let's say you put an insulator between the two. then they would hold the state that you see right here, and there would be a strong electrostatic field between these two charges, but they're kept from coming together and canceling by the insulator that's placed between them. Over on the right side, you see two positive charges. They're lines of flux, or force lines, because they're traveling in the same direction, cannot connect and join together. So when you try to push two like forces together, the fields aren't compatible and they can't cross each other. So in other words, you are actually compressing the field from these two objects as you try to force them together. If you have ever taken two really strong permanent magnets and put one in each hand and held them close to your body so you could steady your hands, in other words, like on your stomach or chest, and then slide them towards each other, at some point you start feeling the resistance. And if you watch, if it's a really strong permanent magnet, you will not be able to push them all the way together. What usually happens is the force of repulsion becomes so strong, pushing back against the muscles in your arms, that it actually is greater, and then your hands slip and they go by each other, because remember, the north and south poles are attracting the same as the two north poles are repelling, etc. Okay, we've talked about atoms and electrons. This is a copper atom. At least it's a graphical representation of a copper atom. I did not draw this diagram. I pulled this off the web. And you see there's 29 electrons orbiting at different levels around the nucleus. The outermost one is the one that we are most excited about, no pun intended. That is the valence electron, or the free electron. So if we look at a copper conductor, which is made up of millions of these atoms, these copper atoms, and each copper atom has a free electron. So we have a very thin density here of copper atoms, but it'll do for our illustration. Now those electrons that have the stars on them, that's the free electron. They are loosely attached to the nucleus. So any energy imposed on this system will cause them to leave their orbit and then pop back in. So if we were to heat up this copper wire, all of these free electrons, the ones with stars on them, would pick up the energy of the heat waves going into the conductor, and they would fly off by something called thermal emission, then they would pop back in. Now electrons are all the same, so it doesn't matter which atom an electron pops back into. You'll see in the next slide that we're going to take and apply a negative and a positive charge. Now remember, the electrons are negative, that's the little dots with the stars, and the nucleuses have a net positive charge. If you have 29 electrons and 29 protons, so you have 29 positive charges and 29 electrons of equal negative charge, it is electrically neutral. So these atoms are electrically neutral. However, if you apply a charge across this conductor, minus to positive, that minus over there represents excess electrons. In other words, they're electrons that have been stripped off of atoms and placed in containment. The positive is a bunch of atoms that are missing electrons. So on the left end of this copper conductor, you have a negative charge, a negative ion, a negative force, which is attracting the protons in all of these copper atoms. Well, the copper is a solid. Those nucleuses are not going to move. This negative charge on the left side is also repelling all the electrons in this conductor over towards the right. Over on the right, you have a positive charge that's repelling all the nucleuses back towards the left, but again, it's a solid, they're not going to move. That positive charge over there is also attracting all of those free electrons. So on the left side, you have an excess of electrons, which are repelling all of those free electrons towards the right, and over on the right, you have a positive charge that's pulling them that way. So I couldn't do it in this graphic, but basically those valence electrons, the ones with the stars on them, are basically popping in and out all the time. They're very loosely coupled, and as they become warmer, you know, the copper wire warms up, they pop in more and out. So when we look at this graphic, here we have a bunch of free electrons that are randomly popping in and out. And if we apply a charge to them, the negative pushes them over to the right, and the positive pulls them to the right. I want to mention that this graphic of the electrons moving through a conductor was not created by me. I added the minus and the plus charges. I got it somewhere off of the internet. But I wanted to give credit. Now this is for educational purposes, so it's okay. But you understand, these free electrons, once they come under the influence of an external minus and positive electrostatic field. Remember, there are lines of force going from that negative charge over to that positive charge, and in the middle are all these loosely coupled electrons that now take off going towards the positive. So that minus and plus could be a battery. Now if you put a wire across the two terminals of a battery, that wire is going to get really hot because you're shorting out the battery and there's too much current flow for that conductor. Speaking of batteries, we briefly glanced at how we could displace electrons with friction and create a static charge. One thing I forgot to mention in the previous graphic, several of those graphics where we were looking at a negative and a positive ion and the lines of force between them, the charge, the electrostatic field between them, the strength of that force that's pulling the negative and the positive charge together is called the voltage. It's measured in volts, and it's a specific amount of force. The closer the two charges get together, the stronger the pull and the higher the voltage. As you move the charges further apart, the field weakens because it has to emanate over a much larger volume, and so you have a weaker field and therefore a lower voltage. So voltage is how we measure electromotive force. It's an electro force that wants to motivate things to move, electromotive force. The invention of the cell, the lead acid cell, which separates electrons from atoms with a chemical reaction, was the first great invention to provide a constant source of electromotive force, EMF, or voltage. By the way, this is a cell and not a battery. A battery is two or more together, such as this. This is a battery of cells. You might also use the term battery when referring to an artillery battery. One artillery unit is a cannon. A group of them is a battery, artillery battery. So now we call cells batteries and vice versa, so everybody seems to know what they're talking about or referring to when they say a battery. But remember, a battery is actually a group of cells. So a 9-volt battery is really a 9-volt battery made up of half a dozen individual cells inside, whereas a AAA, AA, B size, C size, D size, those are literally cells. They're not batteries. Now this particular battery of cells is what was used to power telegraph stations. So this is what powered the telegraph system. Now the way a battery works, or I should say a cell, there's a chemical process that eats away at one side of the cell and transfers negative ions over to the other side, leaving the side that it ate away from positive. Now remember, I told you that there's a force between the positive and the negative charges that's trying to pull them back together. So the chemical force pulled them apart. And in the beginning, when it first starts doing that, it's very rapid. But remember this, as it keeps pulling negative charges away and leaving it positive, the field strength between those two poles on the battery starts increasing. In other words, the voltage becomes greater and greater until at some point the pressure or the force to pull the negatives back to the positives equals that of the acid that's pulling them apart, and then it stops charging. At that point, it is in equilibrium, and that's the highest voltage that that cell can attain. Okay, here we have a loop of copper wire represented by the reddish circle with the blue inside of it. So this is a loop of copper wire suspended in space. And then we have magnetic flux or lines of force that are traveling from the bottom of the image towards the top. Now, remember the influence that these electrons have on each other, that positive repels, negative repels negative, positive repels positive, negative attracts positive, and so forth. So remember, each electron is a little magnet of its own. So if we take an external magnetic field and apply it to that copper conductor, those electrons are going to feel that. However, the electrons are in the loop of wire are only going to move when the magnetic field is moving. So we can move the loop of conductor back and forth through the magnetic field to get the electrons in the loop of copper to move, or we can move the magnetic field in and out of the loop. So I'm going to run this little video clip here. I did not create this, I got this off the web. And what you'll see, you have two graphs there. If you look in the lower left hand corner, a blue and a green. The blue is going to be movement of the magnetic field. Now remember, you could take and hold the copper loop stationary and then take a magnet, like a bar magnet, in your hand and move it in and out of the copper loop or closer to it and further away, and that's one way to get a result. Or you can hold the magnet still, stationary, and then move the copper conductor back and forth in the magnetic field. But when you have a magnetic field, remember that magnetic field is produced by electrons who have all aligned their magnetic polarity to make one big magnetic field. When you impose that on a copper conductor that has free electrons, the electrons in that copper loop are going to come under its influence, but only when something's moving. So if you move the copper wire through the field, then as you move through the field is going to displace those electrons and make them move. If you reverse the direction, then the electrons are going to go in the other direction. Or, instead of moving the magnetic field, move the conductor, and when either way something's moving. Or you can move them both at the same time. Normally you just move one. So think about this. If this were in outer space, you wouldn't know which was moving. You would just see that there's motion between the two. So let's run this little graphic. And first, the magnetic field is going to become more dense, and as it goes in, it induces a current. Notice that magnetic field comes out from the conductor because the electrons are now lined up and moving. Or you can rotate it. Notice the magnetic field that results from the electrons moving in the copper wire. It's interesting to point out that when you use a magnetic field in motion to get electrons to move in the conductor, that electron flow produces now a magnetic field that opposes the one that produced it. It's called counter EMF, CEMF. This takes a little bit of pondering, but the important thing to remember is if you have a conductor and you have a magnetic field and you place them in proximity, if you move one, it's going to affect the other. So you're going to get movement of electrons in that copper wire, whether you move the copper wire in and out of the field or move the field back and forth across the copper wire. That is electromagnetic induction. You're inducing current flow in that conductor because you're passing magnetic lines of force through that conductor, which influences those free electrons to move. And they're all going to move in the same direction because that's based on polarity. So as you slide the magnetic field through the copper wire, the electrons all go one direction, and when you bring it back, they reverse and all go the other direction. That would be alternating current. Okay, you're continually alternating the direction that the magnetic field is moving through the conductor. Therefore, the movement of the electrons in the conductor alternate back and forth. What we have here is a coil of conductor, which is a partial spool of red 18 gauge conductor. Right on the spool it came on, I just pulled the ends off and hooked it up to the D'Arceval meter movement. What you're going to do is watch this needle. Now you can see, just getting the magnet near this coil of wire, you can see some movement of the needle. Now I'm going to slide it inside. You can see that you can almost get the meter to peg. Notice that if I pull it this direction, the current goes one way. If I push it in, it goes the other. If I pull it back and forth, I can keep the current flowing, but it's alternating in direction. It goes first one direction, then the other direction. Now remember that there's a spring on this needle, so it tends to bounce. So let it settle down. Okay, now, so what we have here, this is a very strong permanent magnet. Okay, and that's why I have it taped to the stick, because they're just very powerful, and it's hard to remove them from ferromagnetic material once they attach, and the stick helps. Now remember that inside of this permanent magnet are molecules called domains or dipoles, and each of these molecules have a north and a south pole. In most ferromagnetic material, they are randomly oriented and they cancel each other. In this particular material, this was manufactured as a permanent magnet, so they forced all the domains to be all lined up in one direction and then solidified the material, and that forms a permanent magnet. But the magnetic field from this magnet comes from the electrons in the magnet. And remember, electrons repel electrons. So this copper wire here, you're looking at the red plastic insulation. But inside the insulation is copper wire, and that copper is made up of the copper atoms that we've shown earlier in this presentation. So when I move this magnet in here, the electrons in the magnet, the magnetic field from the electrons in the magnet, repel the electrons in the copper wire. Now another phenomena I want you to notice, I'm going to hold this as stationary as I possibly can, and I'm going to disturb the magnetic field with a screwdriver. Whoop. See how hard that is to get off of there? So I'm going to hold this down a little bit better. And watch the needle. Can you see the needle moving? The needle is moving because when I bring this ferromagnetic material in here, it is intensifying the magnetic field, because the magnetic field moves with less resistance through ferromagnetic material than it does through air. That causes the magnetic field to move. So this is how a proximity sensor works. A proximity sensor actually has a electromagnet, not a permanent magnet, and it has a coil of conductor. And this is stationary, and when a metal object moves by, see the needle moving? When an object moves by, it disturbs the magnetic field, and the current flowing in the sensor amplifier, which would be this device now, senses that change in the magnetic field and says, aha, there's an object there. Another thing to point out is that if I slide the magnet in and out, you see that I can maintain current flow. But I can also move the coil of conductor. I don't have to move the magnet. I can move them both and get a lot. So something has to be moving. If you move the magnet, the electrons in the magnet moves the electrons in the wire. If you move the wire, then the electrons in the conductor moving against the field created by the electrons in the magnet cause current flow. So it doesn't matter which one you move. Move the coil, move the magnets, or move both. Another thing I wanted to show you is, you see, when you have a big loop of wire, you get a lot of heavy action. But if I just pass it by a single conductor, in other words, if I separate out one conductor here, you see the needle motion? Because the magnet only has influence over the electrons in this small area of the conductor, so you only get a little bit of induced current. But when you do it inside the coil, the magnet, the permanent magnet, is influencing all the electrons on this full length of this wire because it's wrapped up in a coil, as opposed to getting just a tiny little deflection on the meter from this motion. In our previous demonstration, we demonstrated electron flow or current flow by either moving a coil of conductor through a magnetic field or moving the magnetic field through the coil of conductor. In the diagram here, we have a single loop of conductor, and in that conductor the electrons are traveling around in one direction, which means that all of their magnetic fields join together to form one magnetic field that surrounds that loop. In this little animation, which I did not create, I got it off of the web, we see what happens when you have many loops of conductor and you have current flowing through it. The individual magnetic fields of the individual loops all join together to make one intense magnetic field, and the magnetic field inside the coil is very intense. This form is called a solenoid, and that intense magnetic field inside of the solenoid is used to attract ferromagnetic material like a rod against a spring to pull it into the center of the coil, and then when you turn the coil off, the spring pulls it back out. So energizing the coil pulls the rod in, de-energized, the spring pulls it back out. That's solenoid motion. Okay, here's another animation that I did not create. I got it off of the web. And if anybody sees their material on here and they want credit, you just email me and I'll put some credits at the beginning or the end. Now here what we have, and I'm going to pause this a minute. Notice that we have a rotating loop of conductor, and at the end of the loops outside the magnetic field there are, we'll call them, if you like, split rings. They're called commutator segments. So the upper end of the loop is connected to the blue piece of metal, curved metal, and the bottom of this loop of conductor is attached to the red. So as the loop of conductor rotates inside of the magnetic field, those commutator segments rotate with it. Attached, or I should say in electrical contact with the commutator segments, are brushes. Those are the two little dark gray rectangles that then have copper wires leaving them and going over to the battery. So here's the idea. With that battery in place, you're going to have current flow. You see positive on one end of the battery. On the other end, electrons are going to flow through the copper wire up to the top, through the brush, into the blue commutator segment, out through the top half of that loop, down the other end, and then back across the bottom of the loop to the red segment, out of the brush on the bottom, through the copper wire, and over to the positive end of the battery. As the current flows through that loop, those electrons flowing through that loop, all of their magnetic fields add together. That magnetic field opposes the magnetic field of the horseshoe magnet, and something's got to move. Since the horseshoe magnet can't move, then the loop moves. So really you could say that the electrons flowing through the loop create a magnetic field on the loop, and the horseshoe magnet, since it's stationary, that forces the magnetic field on the loop, the rotating loop, to move. So let's continue this on, and you see that in order to keep this thing moving, you have to keep reversing the polarity through the loop, because once the loop repelled around in one direction, it would be attracted and then line up and stop. So just as soon as the loop gets in the position to where the north pole has reached, the north pole on the loop has reached the north pole on the loop has reached the south pole on the horseshoe magnet, it would attract and stop right there. Right at that instant, the commutator segments are in a position where we reverse the current flow, and now we've reversed the magnetic polarity of the loop, and so what was attracting is now repelling, and it just keeps going around in a rotary motion. Okay, this looks like the exact same device. Actually, whoever created this animation rotated the horseshoe magnet around perpendicular, and it really doesn't matter because the magnetic field is still passing through the loop, and then they've attached something external to mechanically make the loop move through the magnetic field of the horseshoe magnet. Remember, in the previous animation you had a battery that pushed electricity through the loop, and then the magnetic field of the loop, working with the magnetic field of the horseshoe magnet, forced motion of that loop. So the magnetic field produced by the loop fighting against the magnetic field of the horseshoe magnet gave you your motion. In this case, we're going to do just the opposite. We're going to take an external mechanical means, in this case we'll say a windmill, and we're going to rotate that loop, and as that loop rotates around through the magnetic field of the horseshoe magnet is going to force electrons to move in the loop, and the electrons will flow in one case they'll flow out through the blue commutator segment, up through the brush, down and over through that light bulb, and then back to the bottom into the red commutator segment and back into the loop. So we have a permanent magnet with a stationary magnetic field. We have a single loop of wire or conductor that is rotated by wind energy. We have the loop is extended outside of the rotation by commutator segments. Now if you think about this, the loop that we're inducing current flow into continues through the segments, through the brush, through the wire, through the light bulb, through the wire, through a brush, back into the other commutator segment, back to the rotating loop. So this is really one loop of conductor that includes the commutator segments, the brushes, and the little light bulb. So when we rotate this a little bit later in this animation, you'll see the light bulb will blink as the current is being induced into the conductor. And then of course we'll have rotating in contact with stationary brushes. So the commutator segments are being rotated in contact with the brushes, and the brushes maintain the electrical connection. And then we have a complete circuit through the filament of the light bulb. Remember, the filament of the light bulb is a conductor. So we'll take and rotate the magnet around. We'll get rid of the battery, and we'll replace it with a light bulb, which is a load, and then the air will force the coil to move. That induces current flow. You can barely see the bulb illuminating, but it is illuminating. Okay, this presentation is taking a little longer than I thought, so I'm going to provide an intermission, and we'll just call this part 1. So this is the end of part 1 of Principles of Magnetism and Electricity. And let me remind everyone who is watching this presentation that some of the graphics, some of the images that I used, I got off of the web. In a case where all of the material is not mine, I do not monetize or in any way make any money off of this presentation. And if you want mention of your material, just email me and I will add it to the credits. Right now there's no credits. Again, I thank you for watching this, and be sure to look for part 2, which I will begin working on immediately. Thank you.